Okay, so I want to look at example number 6. So this, sorry. Okay, so this is exercise 2.7. That's the one where it says use theorem 2.5 to determine whether or not these sets of vectors are linearly independent. I'm going to look at the sixth one. There's two of them are labeled number 6. I'm going to do the first one that's labeled number 6. And so we've got 4 vectors, 1, 0, 1, 1, 2, 0, 1, 2, 1, 1, minus 2, minus 2, and 4, 1, 0, 2. And we want to ask whether or not they're linearly independent, and we're going to use theorem 2.5. So basically what that means, or not basically, but exactly what that means, is we want to solve this equation, the one that I am writing now, where we write the 0 vector as a linear combination of these 4 vectors. Okay, and if the trivial solution, that is C1 equals C2 equals C3 equals C4 is the only solution, then the vectors are linearly independent, otherwise they're linearly dependent. And so what we're going to do is what we've been doing, and we're going to put these into an augmented matrix. Now, if you are comfortable row reducing matrices, then feel free to just put this into Wolfram Alpha and have Wolfram Alpha row reduce it, or whatever you want to use. You can, the TI-83s and whatever, use you can row reduce matrices. Okay, so we've talked about this before. I just want to mention it again. When we row reduce this matrix, notice that right-hand side, the part to the right of the vertical bar, that's going to stay zeros. No matter what row operations we're going to do, those are going to stay zeros. So basically, there's no reason to continue to write that down. So instead of continuing to write that down, I'm just going to omit it. Okay, so I want to do row operations. So the first thing that I need to do is I'm going to shuffle the third or the second row down to the bottom. So basically, I'm just going to swap the fourth and the second row, because I need to have, remember, like the second step in this algorithm, and really this should be in the iterative part of the algorithm. At every step in the algorithm, you need to make sure that all of the pivots are underneath or to the left of the pivot in the row above it. But that's not the situation we have here. So I'm going to swap the second and fourth rows. So the first row stays the same. And again, I'm not writing down the column of zeros. Now this is going to be 1, 2, minus 2, 2, 1, 1, minus 2, 0, and then the last row is what was the second row, 0, 0, 1, 1. All right, and now I'm just going to do the row reduction algorithm. So I'm going to subtract row 1 from both row 2 and row 3. So row 1 stays the same, 1, 2, 1, 4. 1 minus 1 is 0, 2 minus 2 is 0, minus 2 minus 1 is minus 3, 2 minus 4 is minus 2. For the third row, 1 minus 1 is 0, 1 minus 2 is minus 1, minus 2 minus 1 is minus 3, 0 minus 4 is minus 4, and the bottom row stays the same, 0, 0, 1, 1. Okay, so now notice that I need to swap the second and third rows to get the pivots right. And when I do that, I'm going to also multiply them by minus 1. So this is 1, 2, 1, 4. The new second row is going to be minus the old third row. So this is 1, 0, 1, 3, 4, 0, 0, 3, 2, 0, 0, 1, 1. Okay, so this is the first pivot to the left. That's the second pivot to the left. The entries underneath all of those are 0, or under both of those are all 0. Now the next pivot is going to be this pivot right here. This is kind of aggravating because we're going to have to do stupid fraction stuff. I have enough trouble doing the subtraction when we're not dealing with fractions. Okay, so I want to subtract 1/3 of row 3 from row 4. So 0 minus 1/3 of 0 is 0. 0 minus 1/3 of 0 is 0. 1 minus 1/3 of 3 is 0. Now 1 minus 2/3, okay? So it's 1 minus 2 times 1/3. So that's 1 minus 2/3. So this is going to be 1/3. Okay, and of course we can just multiply the bottom row by 3 and get a 1 there. That wasn't necessary. And we can also divide the third row by 3 to get a 1 there and a 2/3 there. Okay, so this matrix is in row echelon form. This is in row echelon form. There are no free variables. So the equation, or so the solution, is unique. So there's only one solution. And that solution is the one where they're all equal to 0. All of the coefficients are equal to 0. Okay, and so by theorem 2.5 then, the vectors are linearly independent. And let me just, so that was a solution. That was a solution. Now let me just remind you about how this, one way that this connects back to the initial definition of linear independence. Remember, the initial definition of linear independence was, well, we started with linearly dependent. We said a set of vectors are linearly dependent if one of the vectors can be written as a linear combination of the other vectors. A set of vectors is linearly dependent if one of the vectors is a linear combination of the other vectors. Okay, and if a set of vectors is not linearly dependent, then they are linearly independent. Okay, so how can we use that? How can we connect that to theorem 2.5? What's the connection other than just the proof of theorem 2.5? I want to connect it somehow with this row reduction, which I did in lecture, but I want to do it again here. Okay, so consider the augmented matrix 1, 0, 1, 1, 2, 0, 1, 2, 1, 1, minus 2, minus 2, 4, 1, 0, 2. Okay, consider this augmented matrix. Okay, what this augmented matrix represents is, can the fourth vector be written as a linear combination of the first three vectors? Okay, and if you do the row reduction, notice that that's exactly what we started with up here, except for the row of zeros, but the row of zeros doesn't change anything, okay? So after you do row reduction, what we're going to get is exactly this matrix here. So 1, 0, 0, 0, 2, 1, 0, 0, 1, 3, 1, 0, and then 4, 4, 2/3, 1. Okay, now notice what this last equation says. The last equation says 0 is equal to 1. And there are no coefficients that make this true. There are no choices of C1, C2, and C3 that would make this equation true. So what this tells us is that the fourth vector is not in the linear span of the first three vectors. Okay, and then if you were to say reorder the vectors so that maybe the 1, 0, 1, 1 vector was on the end and put those vectors into an augmented matrix, you would see that the vector 1, 0, 1, 1 is not in the linear combination, or is not in the linear span of the other three vectors. Okay, and similarly for the other two vectors.